It sounds like it's only 4 days of lecture material that we're going through, but let me just quickly remind you, if this were a full semester course, and it really is in terms of the amount of material that you're learning, this would be halfway through the semester. So you've already gotten to the halfway point, so I think it's worth congratulating yourself and really also remembering to keep learning and keep practicing and getting better and better. So before we continue to lecture 4, I just want to say a couple of things. So following the lecture yesterday, we had a discussion across the team, and based on the feedback we've seen, the interest that we've seen, and our own discussions about these things, we've made the decision that all of the lab content and all of the exercises will be made available to all of the students to review and use after the summer school concludes. So this is all because there's just so much interest around this material, and in order to make sure that you all have access to this material, we're going to make it available once the summer school concludes. So that's the first order of business that I wanted to bring up. The second thing that I wanted to bring up is, so we're still in the Discord keeping the lab channels exclusive, but we've also figured out a way to open up the study groups, which I think have been very popular. We found a way to make them open for everyone. So starting later today, there should be, every one of you should be able to see and access the study groups. And my personal recommendation now that you have this access is to take full advantage of the community that's there for you. So talk together, discuss the lecture notes if there's something that you missed. There's some very fruitful discussions that I'm seeing. So please talk to the community that's around you. So the most exciting part of all of this work in quantum education is that we're building a community as we go. And it's great to take advantage of just the amount of talent around you. So please take full advantage of it. Okay, so let's get quickly started. As always, Susie kicked us off on a nice note. What I'll be doing is writing lecture material on the pad that you see here. I'll just quickly turn off my video as I'm taking these notes. I'll keep an eye on the chats to see if something is missing or there are repeated questions about something. And more generally, we'll stop at intermediate points, and Susie, our moderator, will help us with taking questions. So let's get started. Let me just quickly start by turning my video off and sharing my screen with you. Perfect. Okay, so let me remind you again where we are. So this is the 4th lecture. So lecture 4 is the 2nd lecture focused on Shor's algorithm. So this is Shor's algorithm 2. And today what we're going to do is go from factoring to period finding. And using quantum phase estimation and quantum Fourier transform. When I say that, you might remember from yesterday that those two are quite closely related for factoring. So this is the goal of today's lecture, and so I think it's very important before we get started, because there has been quite a lot of material that we discussed so far, to start with a quick review. So walk with me as I do this review. I hope it's a very good refresher for those of you who attended the lecture yesterday. And for those of you who didn't, I hope this brings you up to speed with the material that we covered yesterday. So let me just change the color so that it's easier to distinguish what we're doing. So let's say this is a quick review. What did we do yesterday? So yesterday we learned about the quantum Fourier transform and quantum phase estimation. Okay, so these are lecture the points of yesterday's lecture, and what points did we take away? The first point was that quantum Fourier transform is simply a basis change from the computational basis to the Fourier basis. And in fact, in terms of doing this change in computational basis, what we were saying in the lecture was the following. So the computational basis, for those of you maybe who missed the lecture yesterday, is the set 0 and 1 for single qubits. So let's say for single qubits. This is the computational basis. And in the Fourier basis, what we have are plus and minus. And the transformation from the computational basis to the Fourier basis is exactly what quantum Fourier transform does for us. And of course, you've been practicing with these gates and building quantum circuits at this point. The transformation that allows you to do this in the single qubit case, so the gate that takes you from the state 0 to the state plus, and the state 1 to the state minus is the Hadamard gate. So we also learned that the 1 qubit quantum Fourier transform is the Hadamard gate. Now, this is one of these topics that's worth remembering, because when you see the Hadamard gate in so many quantum circuits, the way you look at how it's being used can be quite insightful if you look at it from different perspectives, and this is one of those perspectives. So a Hadamard gate is doing a one qubit quantum Fourier transform. In terms of how these things work visually, what it meant to do a change in basis from computational to Fourier is the following. So we have a block sphere, not as round as I would like. In both cases, let's do the following. QFT takes you from the basis of states that look like this and this, so either 0 or 1, to states that look like over here and over here. So it's taking you from being on the north and south pole to being on the equatorial plane. And I think this is a very good way to think about the quantum Fourier transform. After doing this, we also learned how to implement the general case of a quantum Fourier transform. So for the 1 qubit case, it's a Hadamard gate. For the many qubit case, we saw that the circuit implementation was the following. So if we have just a box that we call the quantum Fourier transform box, and it takes in several qubits, and it gives us out several qubits of the same number. What is this quantum Fourier transform box doing? If you look inside, what you'll find is, so if we number the qubits 1, 2, 3, all the way down to n, so we're doing an n qubit quantum Fourier transform. Really, what we're doing is applying a Hadamard gate on the first qubit, and then applying these controlled rotations, right? We saw these U rotations, and U rot, when I write it down like this, means unitary rotation. So a controlled rotation with power 2, a controlled rotation with power 3, a controlled rotation going all the way down here with power n. So these are all U rotation gates. And they're all controlled. So there's a control here, and there's a control here. So that's all only for the first qubit. And then we're going to start fresh again for the second qubit. We're going to have a Hadamard gate here, followed by a unitary rotation, again with power 2. And then coming from the third qubit, This is the control, and going all the way to another unitary rotation. Notice how now I have one less qubit to play with, so I don't go all the way up to n, but to n minus 1, and that is controlled by this qubit down here. And that finishes the gate for the second qubit, so we'll close off here and start with a Hadamard gate for the third qubit, and so on. So that is the picture for the quantum Fourier transform. And of course, in terms of gates, you see this thing is composed entirely of these Hadamard and U-rotation gates. The Hadamard you already know, and you're quite familiar with it. The matrix for the U-rotation gate, and when it takes in a power that I've been writing down here as 2, 3, n over here, the matrix looks like 1, 0, 0, and exponential of 2 pi I divided by 2 to the power of k. So k is that number, the argument that the quantum Fourier transform took in. Okay, so when you have this U rotation, you have it, of course, in a controlled way in this quantum circuit. So the controlled U rotation, which I'll call C-rot. So this is controlled U-rot gate. Of course, it needs to know what k is. If it's working on 2 qubits, let's say one of them is 1 and the other is xj, and I'm going to assume when I write qubits down like this, that this is the control and this is the target. So every time you see something like this, it's important to ask what the ordering of the qubits is. So I'm being explicit here and telling you the control is down here, for example, and this is the target. So when the control is active, meaning when the state is 1, what you have is e to the 2 pi I over 2 to the power of k, 1 and xj with xj up here. So depending on what happens, whether xj is 0 or 1, a phase may or may not be applied, but the control allows us to apply this overall phase in the first place. Okay, so that's the first important thing to keep in mind. The second important thing to keep in mind is that you also saw a different way of writing down the Hadamard gate, right? So the Hadamard gate we've seen so far looks like this. And the new way that we've been writing it down is by saying the Hadamard on xj is 0 plus e to the 2 pi I over 2, just 2 to the power of 1, xj, and excuse me, this is 1 over square root of 2. So depending on whether xj is 0 or 1, again, the Hadamard gate would do exactly the operation that you're seeing here. So these are very nice ways to look at the Hadamard gate and the action of the rotation operators. So let me write down these two in boxes, because I think it's very useful to think of how these things are applied. Okay. And another big takeaway from yesterday is that the quantum Fourier transform, so the box that you saw here, that implements, so the circuit that looks like the picture that you see up here implements QFT, but it does this in QFT implemented in reverse order of qubits. So what does that mean? We started with a general expression for the quantum Fourier transform. And so the qubits were numbered 1, 2, all the way down to n here. The general expression for the quantum Fourier transform is exactly the reverse of what this circuit gives you. Okay, so these are the important points in sort of a big summary. I wanted to do one point here and show you something that that's an interesting question that was asked in Discord. So let me first write down exactly what the QFT does. Okay, so what does QFT look like? We said the definition of QFT on n qubits. So n is 2 to the power of n, first of all, where we have n qubits. Looks like 1 over square root of n of, so the first qubit goes to 0 plus e to the 2 pi I over 2x, 1. Tensor product, the second qubit goes to 0 plus e to the 2 pi I over 2 to the power of 2. And then there's x again, 1. And so on until the nth qubit, which goes to 0 plus e to the 2 pi I over 2 to the power of n x, 1. I want to show you something very interesting. So we defined this to be x tilde, right? That was our way of writing the change in basis. So we keep saying there's an x here, right? So there's x here, there's x here, there's x here. So x is involved in all of these exponents. Now, when we write x, I reminded you yesterday that there's this kind of notation that people refer to where x really in decimal is x1, x2, all the way down to xn, where these are bits, right? They're zeros and ones. So when we write down x like this, what's important to keep in mind is that there's always this kind of notation you need to be careful of. Now, notice how in this picture, x is present, which means all of these terms, whether it's the first term, the second term, the third term, and the nth term, excuse me, all of them involve x, which contains all of these elements, right? x1 all the way down through xn. However, if in fact we take a look at what the circuit is doing, I'll show you the circuit here. Look at, for example, what's happening with qubit 1. I'll draw a line here so that you see exactly where I am. Qubit 1 sees a control coming from the second qubit, from the third qubit, and all the other qubits down to qubit n. So it makes sense that there's a term that looks like x, where you have something from x1, something from x2, all the way down through something from xn. Qubit 2, on the other hand, starts off with a Hadamard, and then only sees controls coming from everything below it. So it never sees a control coming from x1. However, if you look at the expression, it actually still contains x, right? So if x contains all of these bits, x1 through xn, but qubit 2 is only getting controls from all the other qubits, how is it that this circuit is implementing exactly what we wrote down for the quantum Fourier transform? And I'll pause here to see if maybe you can take a few seconds to think about why that might be the case. So while perhaps you're pondering on that, let me just explicitly write down what it means to say x or x1 and x2 all the way down to xn. So let me remind you again. So when we write x to be these things, x1, x2, all the way down to xn, really what we're doing is converting between decimal and binary notation, right? So really what we're saying is this is x. So different powers of 2 multiplying the different bits that you see in x. Now, let me show you something really interesting. So when we talk about these things, it's very useful to use concrete examples. So maybe let's talk about the case when we're dealing with n is 5 qubits. Okay, and let's say x is maybe, I don't know, 3. Let's say x is 3. So let's look at what that second term looks like. Okay. So the second term looks like 0 plus e to the 2 pi I. X is 3. over 2 to the power of 2. Okay, so that's what the second term tells us. Let me focus on this exponent just a little bit. So e to the 2 pi I times 3 divided by 2 to the power of 2 looks like the following. So 3 itself is 2 to the power of 1 plus 1. So what you have in this situation is a situation where you have 3 divided by 2 to the power of 2, which you can write down like this. And in the end, this looks like 1 over 2 plus 1 over 2 to the power of 2. Okay? So that's an important point to keep in mind. So the numerator here really looks like e to the 2 pi I times 1 over 2 plus 1 over 2 to the power of 2. Now let's talk about another case. Let's talk about the case where n is actually 8 qubits. So now n is a very lengthy sequence of numbers. And maybe let's say x is 5. Now, what does this picture look like? So again, I'll go back to that second term. The second term looks like 0 plus e to the 2 pi I. X is now 5 divided by 2 to the power of 2, 1. What is 5? 5 is 2 to the power of 2 plus 1. So it's 4 plus 1, right? So 5 divided by 2 to the power of 2, as we see in that exponent, really is the following. And this is 1 plus 1 over 2 to the power of 2. So in this exponent, what we really have is e to the 2 pi I times 1 plus 1 over 2 to the power of 2. Now, you might remember that e to the 2 pi I times some integer, so let's say any integer z, is exactly equal to 1. So because e to the 2 pi I times z is exactly equal to 1, this term doesn't matter anymore. So really, this is equal to e to the 2 pi I times 1 over 2 squared. That 1 goes away because e to the 2 pi I times 1 is exactly equal to 1. Okay, so what have we done though? When we remove that term, because it's exactly equal to 1, what we've done is remove the contribution of some of the qubits to this rotation. So in other words, some of these rotations coming from the qubits that are above you, so if we go back to the circuit, some of the rotations coming from the qubits above you end up canceling out because those rotations are full rotations of multiples of 2 pi. So because of this issue, what you end up is a circuit that looks exactly like what you see here. But in fact, what you're implementing is indeed x divided by different powers of 2. So x divided by 2 to the power of different ranges of powers. So I hope that clarifies to you why the circuit looks like that, even though x contains all of the bits that you see within that circuit. Okay, so this is the kind of question that, this is one of the questions that came up on Discord yesterday. And more generally, I think it's really nice to partake in the community and learn from each other exactly because of things like this. Because you get some insights from people across the world, and it's really cool to discuss these things and gain some deeper insights. If someone hadn't asked that question, I probably wouldn't be going through this. Okay, I hope this is helpful and clarifies the question that was asked in Discord. So maybe let's quickly conclude our review by summarizing what we learned about quantum phase estimation itself. So the first thing that we learned was the quantum Fourier transform. And the second thing that we learned was quantum phase estimation. So maybe let's pause here very quickly before I continue because I see some questions. Susie, Do you think it's a good time to take some questions? How are the questions looking right now?
Yeah, we have one question in particular with the top voted question. So we can start there. Since quantum phase estimation requires knowledge of the eigenvector, which is generally hard to find, is it really useful?
Mm-hmm. There are different ways that you can force the creation of an eigenvector. You don't need to be able to create it on your own. What you can do is force a measurement that collapses you into one of the eigenvectors of the unitary. So that's another way, using measurement, that you can force the creation of an eigenvector that you need to work with for your quantum phase estimation algorithm.
Cool, thanks, Abe. And then it looks like the next upvoted question that's lecture relevant. It says the phase of a quantum state changes during time evolution. It grows as E*T, QPE, applies several gates which depend on the phase theta psi, but there are applied at different times, T. How do you account for the change of the phase over time in the algorithm?
So you're applying, so there's a method called trotterization, and I'll leave a link to everyone. I'll leave a link to everyone so that you can look through the details of trotterization. But basically, what you're doing is effectively applying small time steps of evolution instead of doing one long evolution. So I can post a link to this. That's probably useful for people to see if they're interested in learning things like this.
Great, thanks, Abe. And then the other questions don't have many upvotes. I think if we just continue on with what you were just about to review, that might answer some of those questions.
Sounds good. Thank you, Susie.
Yep.
So we already got a question about quantum phase estimation. Let me just quickly remind you the objective in quantum phase estimation is the following. So if we're given a unitary, U, and remember, we're interested in unitaries here because those are the kinds of evolutions in real physical systems. So if we're given a unitary U and its eigenstate, or you might see in the literature people calling it eigenstate, eigenvector, psi, and the unitary operator we learned yesterday does the following to its eigenstates, right? So it applies onto psi a phase, and we wrote down the phase like this. If the unitary operator is doing this, is there any way for us to find theta psi? In other words, is there any way for us to be able to find that phase that was applied by that unitary operator? So this is an interesting question. So we went with the assumption that we can prepare psi, which, as we just discussed a moment ago, there are many different ways to make this happen. If we can prepare psi, the question now becomes, and we can apply the unitary operator, of course, how do we find theta psi? And the answer was phase estimation allows us to convert this, this phase information. So phase estimation allows us to convert the phase information into things that we can measure. And what are things that we can measure? We can measure amplitudes, right? So phase estimation allows us to convert phase information into amplitudes that we can measure. So what was the protocol? What did we say to do when we wanted to do quantum phase estimation? So quantum phase estimation protocol says, given any unitary such that the unitary applied on some state, let's say phi this time, is e to the 2 pi I theta times phi. Quantum phase estimation gives us 2 to the power of n times theta, okay? And here, N is the number of qubits used to estimate theta. Okay, what does this mean? Notice how, first of all, I wrote down this factor 2 pi up here, right? So what does the circuit do? The circuit says to apply the following sequence of operations. So remember, we said n is the number of qubits used to estimate. So we have n qubits going into, so I'm going to draw them like this. This just means there are n wires here. And they all start out in the 0 state. So I'll write down the fact that there are n of these qubits starting in the 0 state by writing the tensor product like this. And what we're going to do is apply a Hadamard gate to each of these n qubits. That's what this notation means. Then I'm going to take the several n wires. So let's say wire 1, wire 2, all the way down to wire n. And we're going to take the prepared state. So I mentioned to you the eigenstate is phi here. So I'll prepare phi. And I'll say maybe there are m wires involved in preparing phi. I don't know how many qubits it takes to prepare phi. But all I know is that it's prepared for me and I can apply the unitary operator. So what I'll do is apply the unitary operator in a controlled way. So here I'll apply it u to 2 to the power of n minus 1. So that many times. And then coming from the second qubit, I'll apply another control and apply u to the 2 to the power of n minus 2, going all the way down to the last qubit, the nth qubit, which I will use to apply u to the power of 2 to 0th power. And that I'm going to write down here. And the quantum phase estimation protocol tells us if we apply this sequence of gates, let's say the m qubits come out here. At this point, what we have is a quantum Fourier transform of containing information about the phase in its amplitudes. So what we can do is apply QFT dagger here. So that's the inverse of QFT. And go back from, if you remember, what we're trying to do is convert from the phase information that we're looking for here back to amplitudes. And you remember QFT's job was to take us from the up and down, which are the directions that we can measure, to the equatorial plane where you're working with phases. So QFT inverse gives you the opportunity to take advantage of that fact and go back into amplitude. So here, again, you have n wires, 1, 2, 3, all the way down to n. By the end of this sequence, what you should be able to measure is 2 to the power of n times theta. And of course, if theta is a very small number, it helps you to use many qubits to estimate it by multiplying it by 2 to the power of n. So this is a quick summary of the quantum phase estimation protocol. And there are a couple of subtleties to keep in mind as we're doing this. So you might have noticed from your lab that one of the key things to keep in mind here is this up here. So the exponent, I'll write down subtleties. The first thing to watch out for is to notice the 2 pi I times theta. I'll put star here so that it's very clear that I mean a multiplication. So e to the 2 pi I times theta, 2 pi times theta, instead of just theta. So it's important to keep that 2 pi factor in mind. And secondly, notice that we're doing the QFT dagger, right? One of the questions that came up in the Discord yesterday is from people who are doing QFT dagger by hand. So if you're implementing the gates of QFT by hand and you want to know what QFT dagger looks like, let me remind you, so this is not exactly QFT, it's QFT dagger. And the difference between them is that you need to be careful and account for the following. So if you have a series of gates, let's say gate A, gate B, gate C being applied in sequence, the dagger of the entire operation is reversing the order of the gates, first of all, and then applying a transpose complex conjugate to each of them. So if you're taking exactly the sequence of gates that you have for QFT, which we saw up here, the QFT dagger can be implemented by starting all the way from this side and applying all of the operations in reverse, and keeping in mind that you're doing the complex conjugate of those operations, not the same operations. Okay? So this is a very important detail to keep in mind as you're trying to implement QFT by hand. So in yesterday's lab, the solution was to use the U1 gate. In Qiskit, there's a U1 gate that takes in a parameter lambda. And what it does is apply the following matrix: 1, 0, 0, e to the I times lambda. Now, because you are working with a factor here that doesn't have 2 pi, you had to account for this in your work. So if some of you noticed that you had very large phases, it's because of this. It's because of this missing piece. So if you try to account for this 2 pi factor, you'll notice that you get the right answer. Okay. Now, more generally, so there's 2 to the power of n times theta here. What I'm saying is you need to keep in mind that when this 2 pi is not present, you might need to divide out theta by 2 pi. So more generally, quantum phase estimation is an important protocol to know, but there are many different kinds of operators that you can put in here. So the unitary operator that we put in here is the similar to the one that we used in lab, which applies these phases. You can put generally any kind of operator here if you're interested in finding out more information about it. And I strongly recommend at this point taking a look at the chapter on quantum counting. So I'll write it down for you. We have a chapter on quantum counting in the Qiskit textbook, and the quantum counting demonstration does the following. It's exactly what you see here. It's phase estimation, but the unitary operator that you apply here is the Grover operator. It's the Grover rotation operator. And if you remember from your lessons about Grover's algorithm, Grover is effectively doing these rotations, right? So there's some period after, there's some ideal number of rotations that you need to do in Grover in order to find the right answer. So if you keep doing Grover's iterators over and over again, there's some periodicity that you can back out. So I strongly recommend that you take a look at that chapter because we show you using exactly the schematic that you see here with those blocks, the u to the power, different powers being a Grover operator, how you can effectively count numbers. So we call this the quantum counting section in the Qiskit textbook.